Hello everyone! In this lesson, we will continue to study the frequency domain analysis module of continuous system. In this lecture, we will study the Fourier transform of periodic signal. The main contents include Fourier transform of sine signal, Fourier transform of general periodic signal, how to find Fourier series according to Fourier transform, Fourier transform of unit impulse train, and Fourier transform of periodic rectangular impulse train. In order to analyze the spectral characteristic of periodic signal, we should turn Ft into Fourier series. A spectrum is discrete. In order to analyze the spectral characteristic of a periodic signal Ft, we should turn Ft into Fourier transform. It has continuous spectrum. Today, we will discuss the Fourier transform of periodic signal and the relationship between Fourier series and the Fourier transform of periodic signal. Let's start with the Fourier transform of sinusoidal signal. According to Euler's formula, cosine omega 0t and sine omega 0t can be expressed by complex functions. It's known that Fourier transform of constant 1 is 2 pi delta omega. According to frequency shift, we can get the Fourier transform of cosine omega 0t as shown in expression 1. Similarly, we can get the Fourier transform of sine omega 0t as shown in expression 2. Obviously, the frequency spectrum of Fourier transform of sinusoidal signal is expressed by the impulse function. Let's look at spectrum of sinusoidal signal. This is the spectrum of cosine omega 0t. There are two impulses at omega 0 and minus omega 0. The intensity is pi. This is the spectrum of sine omega 0t. There is a downward impulse at omega 0 and an upward impulse at minus omega 0. Well, can we find Fourier transform of general periodic signal? Assume a signal is a periodic signal and its period is 2 pi over omega. According to the exponential form of the Fourier series, periodic signal Ft can be denoted by formula 3, where Fn omega is the coefficient of its Fourier series. According to the definition of Fourier transform, when we solve the Fourier transform of Ft, we can replace Ft with formula 3 and exchange the order of summation and Fourier transform. Then we can get formula 4, which can be abbreviated to formula 5. That is to say, when we solve the Fourier transform of periodic signal, we will find that there is a certain relationship between its Fourier transform and the coefficient of its Fourier series. The Fourier transform of a periodic signal is an impulse train. These impulses appear at n omega. That is to say, they appear at each harmonic. Its intensity is 2 pi Fn omega, so that the Fourier transform of a periodic signal is related to the coefficient of its Fourier series. Through the previous analysis, formula 5 is the Fourier transform of periodic signal. It's an impulse train. At omega equals m big omega, an impulse with an intensity of 2 pi Fn omega is generated. Here you should know that the Fourier transform of the periodic signal is represented by the spectral density function. It's a continuous function, but it shows that in the infinitesimal frequency band, the harmonic frequency point reaches its infinite spectrum value. It is expressed by impulse. Since the Fourier transform of periodic signal is related to the coefficient of its Fourier series, then can we find the coefficient of Fourier series according to the Fourier transform of periodic signal? If f0t is the principal value period of periodic signal, f0j omega is the Fourier transform corresponding to f0t. The Fourier transform of f0j omega is shown in Formula 6. This is the Fourier transform of its principal value period. Let's look at Formula 7 and Formula 8. Formula 7 is the expanded formula of the Fourier series of the exponential form of periodic signal. Formula 8 is the coefficient of Fourier series. Let's look at Formula 6, 7, and 8. We can find that in the principal value period, f0 and ft are the same. Then, when omega equals n omega, the spectral coefficient fn omega of the periodic function f0t can be solved from f0j omega. As shown in Formula 9, obviously, the spectral coefficient fn omega is equal to f0j omega over t when omega equals n omega. This is the relationship between Fourier coefficient and Fourier transform. Let's take a look at Fourier transform of unit impulse train. Let's first look at the mathematical model of unit impulse train as shown in Formula 10. This is its time domain waveform. Obviously, it's an impulse train. Because the Fourier transform of delta t is 1, obviously, Fourier transform f0j omega of its principal value period is 1. According to Formula 9, the spectral coefficient of Fourier series of delta t should be 1 over big T. Then Formula 11 is true. This is the expanded formula of Fourier series of the periodic unit impulse train. This is its time domain description, and this is the expanded formula of its Fourier series. Let's take a look at a spectrum. According to the relationship of Fourier transform and the coefficient of its Fourier series, as shown in Formula 5, because here fn omega is 1 over t, obviously Formula 12 is true. Let's take a look at a spectrum. Figure 5 is the waveform of its spectral coefficient. Figure 6 is the waveform of its spectral density function. This is an impulse train. The impulse appears at n omega, and its strength is also omega. Let's look at the Fourier transform of a periodic rectangular impulse train. This is its time domain waveform. Its principal value is from minus tau over 2 to tau over 2. In the same way, we first find a spectrum coefficient according to the Fourier transform of principal value period, and then find its Fourier transform. We know that its principal value period is a rectangular pulse. Its Fourier transform changes according to the law of sampling function, as shown in Formula 13. According to the relationship between f0 and f, as shown in Formula 8, and according to Formula 5, then we can get Fourier transform of a periodic rectangular pulse as shown in Formula 14. Obviously, the spectral density function of the periodic rectangular impulse train is also an impulse train. Of course, its impulse intensity changes according to the law of sampling signal at different n omega. In this lecture, we analyzed the Fourier transform of general periodic signal, including Fourier transform of sinusoidal signal, Fourier transform of impulse train, Fourier transform of periodic rectangular impulse train, and Fourier transform of general periodic signal. Finally, we discussed the relationship between Fourier coefficients and Fourier transform. So much for today. Thanks for your attention. Goodbye.